Bismillahirrahmanirrahim. Good evening, everyone. Today I will try to illustrate the important sides about the laser diffraction, okay? Or how we can determine the width of single slits by using laser diffraction. Here we have three purposes today. The first one, to measure the width of a single slit by using known wavelength. Should be know the wavelength of the laser. Which laser we will use, we should know its wavelength. Actually, in this experiment, we will use helium neon laser with 630 nanometers, okay? And we can use, by using the same way, we can use the diameter of a tiny wire. It's a very, very small wire, electronics copper wire, let me say. And if we know the diameter of this wavelength, I'm talking about the third purpose, or if we know the width of this single slit, we can know the wavelength about the used laser, okay? By using the same equation, this equation will be the Bragg's equation. It will illustrate to us the relation between wavelength and a specific distance between some patterns after the laser diffraction happened. Here, at first, let's talk about some important properties of this laser and why it's featured according to the ordinary light. This laser, actually its amplification light is stimulated by using some emitted radiation. That's mean it's a lot of light, let me say, with same wavelength and the same direction to can generate intensity like that. Okay, we have two important conditions, must be with the same wavelength. For example, I use this laser, the green laser here with, it's written there 532 nanometers. That's mean I have a lot of lights with the same 532 nanometers to can amplification this light to be like this with high intensity with the same, because all of these emitted rays with the same direction. Okay, it's electromagnetic radiation as visible light because we can see it. The difference, because that we use it as a pointer. The differences between the ordinary light and laser are, here we have some important characteristics. Laser is a coherent light, okay? Its photons have the same wavelength, like I said before, phase and directions. High intensity, because we can use it as a great pointer. It's a good option. Best option, actually. Very low diffraction. That's mean it has a diffraction like a light, but the ratio between them is huge, okay? By using a double slit, we could use a diffraction, we could say a light diffraction by use double slit experiment. You know it, but I'm talking about the distance between these two slits. It was bigger, it was huge according to our experiment, okay? I will illustrate that better in the next slides. Very low diffraction, it can deliver a high energy at a short time because that in another sites, it's used as a weapons. Here, at your specialist, at your department, the dentists are using this laser to whitening teeth, to treat some teeth decay. Here in this picture, the dentist used it as a sharp knife to cut something and at the same time benefit from its high energy to kill any germs, to kill any bad bacteria can happen. That means it's a tool with two benefits, as a sharp knife and as a, let me say, as an antibiotic or colonia. Here to dry the what you will put about, I'm talking about the composition component. You will use it to fill the cavities. Here, this laser, it's not UV because it's a visible range. You can see it. The dentist is using to dry these compositions. Here, as a drilling, we talked about some material. The dentist use it because your teeth bulb, it has a high sensitivity to temperature increasing, because that you use a specific material, specific stone. Here, you can use a laser drilling, okay, with the same purpose. Sure, here the energy, it's different between the bite whitening tool and tooth drilling. Here, the energy is different. Here, you can use as drilling. Here, you can use just to take the first layer of the patient's teeth, okay? That's mean that has strong relation with the equation about energy, has a specific relation with wavelength. Actually, linear relation, but inverse. When you increase one of them, the other will decrease. That's mean to use this laser as tooth drilling. That's mean you must use laser with high energy. That's mean low wavelength, okay? Here, what we will use, I'm talking about the tools, helium neon laser with known wavelength, that means 630 nanometers, screen to can see the patterns, the laser diffractions, single slits to determine the width of this single slit, ruler to know the distance between them, because the distance between the single slit and the screen will be important. We will use it and to measure the width of this single slit, or to measure this diameter of this teeny wire. Here, let me talk about, let me illustrate the Bragg's law. N lambda equal d sine theta, and that means the patterns. How much patterns I have, how much light or dark patterns I will have after the diffraction laser happens. Here, for example, I have from left or right, there will be the same like the when I was talking about the lens, focal length or focal point to any lens, from in front or behind will be the same, okay? Here, the same thing, from right or left will be the same, because that's up to you. For example, here, 1, 2, 3, 4. That means I have 5 patterns. 3 patterns, sorry, because here will be our original point, like 0, 0 in any 2-dimension curve. Here, that means I will start to calculate from this first light pattern. Here will be N1, N2, N3, okay? When I have N1, that means I have X1. What is the X? X is the distance from the center. That means from the bright spot, the original one, to the N1. That's mean here the distance between the bright spot to N1. X2 from the bright spot to N2. And the same thing with X3. That's when I have, that means when I have 3 patterns, N1, 2, 3, that means I have 3 different distances, okay? Here, and it's clear, lambda is the wavelength of used laser helium neon with 630 nanometers. D is the distance of this, or it's the width of this single slit, or it's the diameter of used wire. Okay. Sine theta is the angle. Here, at very small angles, like this situation, we can say, instead of tan theta, sine theta, okay? From here, from theta dash to theta, we can convert it because it's approximately the same. By that, we can say sine theta equal x, the distance between the bright spot and the other pattern, divided on the distance between the screen and the width of this slit or the diameter of this wire. It's very important because that's here, it's d small. In this solved example and the next solved example, I used 1 meter. Other doctor used 135 centimeters. Other used 80 centimeters. It's different, okay? By that, here, all these Bragg's law elements are clear. We can go to the next slide. And let that equal d sine theta. We need to calculate the distance or the width of this slit or the diameter of this wire. That's mean we will focus to determine, to calculate this d simple. And the patterns number, how much I have. For example, here 1, 2, lambda is constant because we used helium neon. Sine theta, we don't have theta because that we can't calculate sine theta, but we have another trick, math trick, by saying theta dash approximately equal theta. By that, sine theta equal x divided on d, okay? X, we could calculate it by using this experiment in our lab and use this ruler and this kind of paper to can calculate the distance between these patterns. Approximately, it's 1 millimeter, the distance between each n. Okay, that's mean from n1 to from spot, bright spot to n1 equal 1 millimeter. From bright spot to n2 equal 2 millimeters, and goes like that. Okay. Here, by that, equal n lambda equal d between two brackets x divided on d. To simplify this equation by using graphical side, by say n will be at y-axis, the pattern number 1, 2, 3, 4, whatever, and the distance between them will be at x-axis. Slope equal n divided on x. By that, we can say slope d, the distance or the width of this slit or the diameter of this wire, used wire, equal slope multiple wavelength multiple the distance between the patterns, the screen, and the width of this slit or the wire. Okay. Here, it's a great picture. I take it from Google. But here, the source used D capital. We use D small here. Be careful. We calculated the D small. That's mean the width of the slit or the diameter of used wire. Here, it's the D capital in our work. From the screen to the slit. Here, these patterns, light and dark patterns, we calculated the distance, I'm talking about x1, 2, whatever, between the dark patterns to the next. From this point to this dark point, dark pattern, it was approximately 1 millimeter and goes like that. Here, the relation between the intensity and its position, intensity will be at y-axis and the its position, its theta will be at x-axis. Here, the bigger one acts to the bright spot at the center, to this bigger bright spot. Here, after did our experimental, after did the diffraction laser by using very tiny wire, we watched, we have this pattern shape in the screen like that. Actually, this link, it's belong to great video, very helpful. I advise very too much to my students to watch this video many times. This doctor could summarize this experiment very well. Here, the width of the single slit. Here, it acts at before this slit, before this width, before this D small. The laser acted as a particles. It was walking as arrows, okay, like the bowling balls. After this very teeny point, a very teeny spot, what I should say is, yes, very teeny opening point after this very teeny hole. It changed its behavior to act as a waves. We can say this very small point or this very teeny diameter, if I used wire, could divide the wave direction to two sides and make from these two sides as two light sources. Each one could generate a waves like that. By that, we had interference and collapse phenomena because that we have these interference patterns. Okay, I'm talking about the light and dark patterns. That means without pressure to the light acted as a waves, we can't illustrate, we can't explain why we have results like that, okay? Here, it's this curve from my MSc thesis, but I used X-ray diffraction, the same idea, but by using different source. Here, the intensity at y-axis and its position at x-axis by using original program to plot this curve, okay? Here, let's come back to our example. Determine the width of single slit, or I can say determine the diameter of a thin wire. I used it to generate laser diffraction by using helium laser. That's mean its wavelength, you know it. Actually, it has 630 nanometer. According to the column and X, the distance between the patterns below, when the distance between the slit and the screen is 1 meter. That's mean 100 centimeters. Here, by using Bragg's law, n lambda equal d sine theta. Like I said before, when theta is very small, I can say sine theta equal x divided on d. To use this trick, because I don't have theta, that means I can't calculate sine theta equal what? I put it another elements equal this value. That means L lambda equal d x divided on d. Now, by putting n here to be n divided on x, multiple lambda, multiple d equal d small, what I should calculate, the width of this single slit or the diameter of this thin wire from graphical side. But here we have another problem. I have three patterns value or patterns number, n1, 2, 3, 4, and its positions. 1 millimeter, 2, 3, 4, like is written there. By that, I can't use the average value. because n, it's a number, not a value. I can't say 1 plus 2 plus 3 plus 4 because 3 or 2 is the pattern number, not its value, okay? X is the distance between them, but I can't solve this problem by using another math trick, by using graphical side. Here, when I say, or actually I know n at y-axis and its distance, pattern distance at x-axis from slope, from triangle rule, slope here equal n divided on its distance. By that, I can put slope here to be distance equal slope multiple noun lambda multiple the d capital, the distance between the screen and the slit, single slit. By that, here, slope equal 1, but it has a unit. I should use it to can prove the diameter its unit will be millimeter. Okay, here we have important thing. All these units are different. Here nanometer, here 1 divided on millimeter, here centimeter. We can't calculate these numbers directly because I'm talking about the unit. The unit will be not acceptable. The number will be not acceptable. By that, let me summarize that. 1 divided on millimeter. Here, nanometer to be millimeter will be multiple to 10 to force minus 6. Here, 100 centimeter. To convert it to be millimeter, I will multiply it to 10. To can say millimeter here will go out or cancel this millimeter, and the last result will be just millimeter. The width of this single slit or the diameter of this tiny wire is just 0.63 millimeter, 0.63 millimeter. Okay. Our conclusion, the relation between the patterns number at y-axis and the distance of these patterns at x-axis is a linear direction. That's mean when one of them increase, no, its kind is directional. When one of them increase, the other will increase too. That's it. Thank you about your watching, your listening. You have a good day and see you in the next video. Oh.